Well, welcome everyone to the last day of the conference. Our first speaker will be Thomas Vidick from Caltech, who will tell us about how entanglement is helpful for multiple provers.
All right, thanks, Aram. Is the mic good? Yeah. So good morning, everyone. Thanks for joining me at this early hour on the last morning of QIP. I appreciate the company. Of course, it's a pleasure to be here. So I'm going to be talking about joint work with Joseph Fitzsimons, who's at Singapore University of Technology and Design and Center for Quantum Technologies. So the main result of the talk is in the title, so you all know it now. There's not much suspense left. This should work. Sorry, it worked earlier. I guess I can use the computer. All right, okay, it works now. I'm sorry. So here's the outline for the talk. So what I meant to say is that I'm going to spend some time giving a fairly lengthy introduction before I go into the details of the results. So this introduction will go, we'll try to be thinking about the question of what it means to locally verify classical or quantum proofs. So we'll discuss that, and we'll discuss it in the framework of multiplayer games that I'll introduce. Then I'll describe the result, and I'll give you some elements of the proof of the analysis of this game for the local Hamiltonian problem. And then I'll end by describing some implications of the results for first the quantum PCP conjecture, and second quantum interactive proof systems. So let's start slowly. Let's start with classical proofs. So you're all, I assume, familiar with the class NP. So that's the class of all languages for which membership can be decided efficiently given access to the correct proof. So there's many such languages, some of which almost all of you probably are familiar with. So for instance, in this problem, the X is a graph, and the property is whether the graph is 3-colorable or not. And so given a proof which would be a 3-coloring, then this is efficiently verifiable. There's other types of problems. For instance, one that's closer to physics, the Ising spin problem. You'd be given instance of Ising spin, so just an interaction graph, and the property that you're trying to decide is whether the ground state of that instance has energy below a certain threshold. So that's problems you're familiar with, and then there's a lot of other problems that maybe you know less. So I just put the names up here. I'm not going to explain what these problems are. It's not important for the talk. The reason I'm putting the names up is just to try to remind you, sort of put you back at this early time. It's probably a bit hard, but how amazing the Crook-Levin theorem is. Because what the Crook-Levin theorem says is that this class NP that has such amazingly diverse problems as those that I listed up there also contains complete languages. And in fact, all the languages, all the problems that I put here are NP complete. And what this means is that every single one of them is just as hard as all the others. So for instance, if you're interested in solving chromatic number, you can transform the instance in an instance of Super Mario, and then you can solve the Super Mario instance, and this will give you the answer of whether the graph was 3-colorable or not. So a bit more concretely, for our purposes, what the NP-complete problem we're going to use is 3-SAT. And so, for instance, given the graph, you can always transform it into a 3-SAT formula such that the graph is 3-colorable if and only if the graph is satisfiable. So one first consequence of the theorem is that there's NP-complete languages. The second consequence is that all these languages, all these problems in NP can be verified locally. So in the following sense. So imagine that you're Arthur, pretty young, not so strong yet, and you're trying to decide whether a graph that's given to you is 3-colorable or not. So the first thing you can do is transform that graph into an instance of 3-SAT. So now you're trying to decide whether this formula is satisfiable or not. And then if you have access to some all-powerful Merlin, Merlin can come up with a satisfying assignment to the formula. He can give it to you, and that assignment you can check locally. And following the following procedure, you just go through the clauses one by one. Each clause acts on 3 of the variables. You look up the 3 variables, you check whether the clause is satisfied or not, and you do this for all the clauses. And if it works for every clauses, then you've decided, verified that the 3-SAT instance was satisfiable. So now, is this really a local verification procedure? Not really local, right? The sense in which it's local is that every check that you're making only requires you to look at 3 bits of the proof, but then you still need this whole proof to be there in principle, right? You have to physically store it somewhere and then query all these bits. So what if we try to make this into a completely local procedure? So let's just leave the proof to Merlin, and instead we just ask him directly the questions. So we take this clause there and we ask Merlin, look Merlin, I mean, what's the value of variable x3 in the satisfying assignment that you're claiming exists? And Merlin will say something, and then we ask him x5, x8, and then we check, and if they satisfied our clause, we're happy and we move on. So does this work or not? Of course it doesn't work, right? Because the issue is that Merlin here is asked the three variables. Once I've arrived at x8, he knows exactly what clause I'm interested in. And so if he's trying to convince me that the clause is satisfiable, he can just tell me whatever value I should assign to x8, in that case a 0, in order to make the clause satisfiable. So this doesn't work. It seems that we really need, even though I'm claiming this is a local procedure, I really need the proof to be there physically. I need it to exist. If I'm just asking the questions to Merlin, he can adapt his answers in order to fool me. He'll convince me that the formula is satisfiable always, even when it isn't. So it turns out there's a very nice way around this, a way to make proof verification completely local, and that involves using not one but two Merlins. And I'm going to phrase this verification procedure as a game, but think of really Arthur is trying to decide whether a 3-sat formula is satisfiable or not, asking questions to two different Merlins. So we'll call, or I'll be calling sometimes Arthur the referee of that game, and the Merlins, I think of them as players. They're trying to win the game. They're trying to convince Arthur that whatever property he's checking is satisfied. And so the game proceeds like this. Arthur just selects a pair of questions, send them to the Merlins. Each Merlin gets his question, provides an answer, and Arthur checks these answers according to some checking procedure that he has in mind. And so we're assuming that the rules of the game are public, and the Merlins, they always try to win in this game. The only restriction is that they don't communicate, right? So each of them sees his own question and provides an answer to that question. So there's just one quantity that we're going to be looking at throughout the whole talk, and that's the value of the game. It's simply the maximum success probability of the Merlins. So I'm maximizing over all possible strategies for these Merlins of the probability that Arthur accepts their answers. So let's do an example, relevant example. Let's do a game for checking 3-sat formulas. It's called the clause versus variable game. So here's what Arthur does. He takes his 3-sat formula, he chooses a clause as before, and then he also asks the first Merlin for an assignment to the variables that show up in that clause. And first Merlin is going to say something that satisfies the clause, obviously. There's no reason for him to say something that doesn't work. But then the trick is that Arthur is going to use the second Merlin. Now he's going to ask him just one of the three variables at random and ask him for the value, what's the value of that variable in the satisfying assignment. And second Merlin has to say something. And then Arthur is going to check that the answers from the first Merlin satisfy the clause, and the answer for second Merlin is consistent with this Merlin's corresponding answer. And so in that case, they're failing, right? You can see they're not consistent. Arthur is going to reject them. So what I claim is that this game or this proof system is sound for 3-sat, meaning that if the formula is not satisfiable, there's always going to be a question such that the Merlins are caught on that particular question. The way to see it is that if you think about what this guy is doing, he's only asked variables one at a time. So what's the strategy for him? What does he have in mind? He must have an assignment to all the variables in his mind. And if I ask him for the 8th variable, he just answers me the 8th value here. And if I'm checking for these answers to be consistent to these answers, even if this forces this Merlin's answers to be consistent in between themselves, and because they have to satisfy all the clauses, they have to satisfy the 3-sat formula. So we have this very important property that we were looking for before, which is that if the formula is satisfiable, then the Merlins have a perfect strategy in the game. That's pretty clear. But also conversely, if the Merlins have a perfect strategy in the game, then the formula is satisfiable. And for this, we needed these two Merlins. And so one way to phrase this, I mean, this is very informal, but and it's just an observation, but the consequence of that observation is that if Arthur is trying to verify membership in an NP language, he can do this now using a truly local procedure in a certain sense. He doesn't need to store any proof. He just needs to query two separate Merlins, get the answers, check, and this is going to work out. Now, you might complain a little bit about this result because there's one problem to it, which is that if only one of the clauses is violated, if there's an assignment that satisfies everyone but one of the clauses, then there's very small chance that Arthur picks that clause, or at least he's going to have to go over all the clauses in sequence. It's going to take him a lot of time. There's still going to be a lot of communication involved. So it turns out even that you can get around, but that's a much deeper theorem than what I've showed you so far, Pcp theorem, Some of you have seen it before. This theorem says that if you're, Arthur can do some pre-processing. So he's given this 3-sat formula, phi, he can transform. You can think of this at the level of the formula. So he can transform the formula into a formula such that if before it was satisfiable, then it remains satisfiable. But if before it was not satisfiable, then now the best assignment has to violate at least, let's say, 10% of the clauses. So now if the best assignment satisfies 10% of the clauses, Arthur can just choose a clause at random, ask the questions, and then if that is the case, then the chance that the Merlins fool him will be only 90%. That's still high, but you repeat it a few times, you can boost this to a good success probability. So that's all very well-known results in the classical world, and now I want to try to go through the exercise that John Smolin went through yesterday. Let's put quantum in front of everything and see what we can say about it. So let's do it. So what is known about the same kind of questions, but now we're interested about quantum proofs. So of course I'm talking about the class QMA, the class of languages that can be decided efficiently given access to a quantum state of polynomial size. So this class also contains a lot of interesting, diverse problems, not as many as NP, but then it's a class that was introduced more recently. I listed some examples here. And we also have an analog of the Crook-Levin theorem, so it's sometimes called Kitaev's theorem, which is to say that one of the problems, the 3-local Hamiltonian problem, is complete for QMA. So I think a lot of you already know more about this problem than I do because you went to Itai Arad's tutorial on Saturday, but I still want to remind you of the definition. So what's this local Hamiltonian problem is going to be important for the talk. So what you're given as input is a description of a local Hamiltonian. So this is just given to you as a sum of matrices. Each of these is Hermitian. I'll assume it's positive, semi-definite, and acts on only 3 qubits, meaning that by itself it's just an 8x8 matrix. And the total Hamiltonian is the sum of these matrices tensored with the identity on the qubits on which they don't act, I'm sorry. And the problem is to decide whether this Hamiltonian, between 2 possibilities, there's a promise that one of them holds, either the Hamiltonian has a ground state, or let's say there's a vector such that the Hamiltonian has overlap with that vector less than some threshold A, or all states have energy at least some other value B with respect to the Hamiltonian. A and B could be anything. I just gave you some sample parameters to think about here. You can really allow A to be extremely small. So you can think of A as being an exponentially small quantity, and B is also small, but it's still kind of significantly above 0 in the sense that it's inverse polynomial. So this problem is complete for QMA, which means that we have the same picture as we had before. We have Arthur. Now Arthur is a quantum procedure, and he wants to check one of these QMA complete languages. For instance, he's given a unitary. He wants to check if this unitary is close to a multiple of the identity or not. The first thing he can do is he can transform this efficiently on his computer in an instance of the local Hamiltonian problem, such that now he only needs to check whether this local Hamiltonian has a ground state with low enough energy or not. And if he has access to a quantum Merlin can give him the quantum state, which would be the ground state, and then he'd pick one of these local terms, look up the 3 corresponding qubits, measure the term, estimate the energy, maybe repeat this sufficiently many times, so he might need many copies of the state, but I'm sort of ignoring this for now. And then he'll be able to verify that the energy is sufficiently low. But again, this is not truly local because we need the state to be there. Even though we're only checking 3 qubits at a time, I need to store it physically and then access the qubits. And if I try to give the state back to Merlin, I'll run into the exact same problem as I had before. So this is not truly local in our terms. And the question that I want to think about in this talk is whether we can achieve truly local verification of quantum states in the same way as we just did it in the previous slide for classical proofs. And we're going to try to do this using the language or the framework of quantum multiplayer games. So here's my quantum. So what are those? Just the exact same kind of games as before, except now I'm making everyone quantum. So Arthur is a quantum polynomial time machine, and the Merlins are, anyways, all-powerful quantum. So Arthur interacts with the Merlins, he sends them questions, but now these questions can be quantum messages. So think of him as preparing an arbitrary quantum state and then sending parts of it to one Merlin, parts of it to the other Merlin, and maybe he's keeping the remainder for himself. Then the Merlins get their states, they do some quantum operation, some unitary, some measurement, whatever they want, and they send some qubits back to Arthur. And then Arthur receives those and he makes a measurement on everything that he's kept so far. And this, based on the outcome of that measurement, he'll decide to accept the answers from the Merlins or reject. And so one very important point about these games is that since we're allowing everyone to be quantum now, it seems to make sense, the Merlins are quantum players, it makes sense to allow them to use entanglement. So I'm assuming that they can initialize their own private spaces in an arbitrary entangled quantum state. But then once they receive their questions, they're restricted to local operations on their respective shares of the entangled state. This can involve, local unitaries or local measurements. All right, so that's the setup. And just as before, we can define a value of a game. I'll denote it omega star. The star refers to the entanglement and the fact that it's a quantum game. And this is just the maximum or supremum, because of the maximum might not be achieved in general. So the supremum over all possible strategies for the Merlins of their chance of being accepted in such a game. So what have we done? In moving from the classical framework to the quantum framework, we've done two different things. So the first thing that we've done is we've allowed Arthur to be quantum. Before he was classical, now he has a quantum machine, he can send quantum messages. That's clearly giving more power to Arthur. In particular, if we want to simulate a classical game in this framework, you can always imagine that Arthur sends only classical queries and measures whatever qubits he receives in the computational basis. So he's kind of forcing the Merlins to be classical. So these quantum messages, they're giving more power to Arthur, it seems. That's the only thing they're doing. But in fact, we know from an older result by Kobayashi and Matsumoto that if that's the only change that we make, so putting the entanglement aside, I'm not changing the power of Arthur. This quantum is actually not useful. The only thing he can do in this framework with no entanglement is verify languages in NP. That's it. No more power than classical Arthur. Quantum messages are useless. But we did another transformation, which is that we allow the Merlins to use shared entanglement. And so the effect of that is that Merlins have more power now because they have an entangled state, they can make measurements, they can achieve higher correlations, and using these correlations, they can increase their chances of winning in the game. And that's exactly what we said when we say that quantum mechanics, there's Bell inequality violations. It's saying using entanglement, you have correlations, you can achieve correlations that you couldn't achieve without. But the question we're going to look at in this talk is, okay, could it also be giving more power to Arthur? So in a sense, Arthur knows that these Merlins are using entanglement, right? So could there be some games for which this entanglement is used by Arthur in the sense that he's asking the Merlins to use their entanglement in order to convince him, for instance, that an instance of the three-local Hamiltonian has a ground state of low enough energy. So the question is, if you don't have an entanglement, just quantum messages, you're limited to NP. Now you give entanglement to the Merlins, it seems they're only going to use that to fool you, and I want to ask, could Arthur be using this entanglement to decide languages that go beyond NP, so QMA languages? All right, so let's think about this. Before going into there, I want to deal with the first problem, because the first problem is saying, can you even verify languages in NP? Is it not the case that now using their entanglement, the Merlins are going to break this clause versus variable game that I introduced before? So let's briefly look at this. Remember the game. So Arthur has a three-stat formula he wants to check. He picks a clause at random, sends the clause to the first Merlin, one of the variables to the second Merlin, gets answers back, and checks that the first Merlin's answers satisfy the clause and the second are consistent with the first Merlin's answers. And what we saw is that if everything is classical, there's no entanglement, then the game has value 1 if and only if the formula is satisfiable. Now I give entanglement to the Merlins. What happens? Well, this breaks down. So there's examples you can come up with. This is based on an example by Mermin and Perez called the Magic Square game. You can construct a simple three-stat formula. It has 9 variables, 24 clauses, I think. And this formula is not satisfiable, but the Merlins can win the game with probability 1 using their entanglement. It's not so surprising. I mean, this is a Bell inequality violation. We've seen these before. Perhaps we shouldn't be surprised. But in terms of complexity theory, it has a dramatic consequence, which is that it's not clear anymore now that these Merlins are any useful to Arthur. Can he do them to do anything else that he couldn't do by himself? Can we go beyond P? And so the answer, oh sorry, I meant to show this before. The answer is that yes, and I'm not going to go into that. This is prior work by Ito, Kobayashi, and Matsumoto. So you can design a slightly more complicated game. It's not very different. The only thing you change is the question to the second Merlin. Instead of asking him one variable, you ask him two variables chosen in a certain way. And that new game will preserve the soundness. So it'll have the property that we had before, even if the Merlins use entanglement. So in this model, with entanglement, you can still verify NP languages. And our question is, can you verify QMA languages? So let's try to do this. I think this is a fun question. We're taking a QMA complete problem. Let's try to take the local Hamiltonian problem, and let's try to do the exact same thing. Let's try to design a game for the Merlins to convince Arthur that the instance of the 3 local Hamiltonian is satisfiable. So can we design a Hamiltonian versus qubit game in the same way as we had a clause versus variable game? So this is what we're trying to do. And how would we do it? Arthur is there. He's given his instance. He's going to pick one of the local Hamiltonians. He has access to the Merlins. He'll ask the first Merlin for the qubits on which this Hamiltonian acts, and then he chooses one of the 3 qubits at random and asks the other Merlin for it. And presumably what we're asking these Merlins to do is that each of them should have a copy of the ground state, and then the first one gives us back the 3 qubits that we asked about, and the other one sends us back just this 1 qubit that we asked him about. And so the question is whether this works. So there's some it doesn't, to give it away. And there's some immediate difficulties. The first most obvious difficulty is, how do you do this consistency checking that you were given before? What does it mean to be checking that, the first Merlin's qubit number 8 is equal to the second Merlin's qubit number 8? I mean, this state can be entangled. In principle, these are reduced density matrices. You can't check the 2 reduced dense. For all we know, they're just a totally mixed state, right? And there's no way to check that this is totally mixed state and this is also the totally mixed state. So we can't check that they're the same. There's a much deeper issue, which is, even if we could check, we're just checking that these 2 states that these Merlins have in mind are kind of locally equivalent. They have the same reduced density matrices. But whether these reduced, we know that, we're all familiar with many examples of states that have the same reduced densities locally but are different globally. Something that happens quantumly but didn't happen classically. So even if we could check this just wouldn't work. It's not enough to check that the states are equal locally. And there's a much deeper objection that I gave you on the previous slide, which is that this just cannot work under complexity theoretic assumptions, because in my proof system here, I'm not asking the Merlins to use entanglement in order to convince me. And I know that if this is the kind of setup I have in mind, the only languages I can verify are NP languages. So unless NP is equal to QMA, this just simply cannot work. We have to do something different. All right, so here's an idea. Because the Merlins should be using entanglement, the natural idea is to ask them to somehow split the ground state in a certain way, and then we'll be asking the first Merlin for some of the qubits of the ground state and the other Merlin for the some of the other qubits. So how would that look like? To make it simple, let's assume that the Hamiltonian is one-dimensional Hamiltonian, so it looks like this. This is your qubits. Then the Hamiltonian has terms that act on these pairs and then terms that act on, so it's a nearest neighbor Hamiltonian in 1D. So then a nice idea would be, well, let's ask the Merlins to split the proof. So we'll give the even numbered qubits to the first Merlin and the odd numbered qubits to the second Merlin. So they kind of split it like this. Now there's only one proof. And now I can still check my Hamiltonian because each of the terms acts on 2 neighbors. So for instance, I take the 4th term, it acts on qubits number 4 and 5. I can ask them for each one of them for one of the qubits, get it, check the energy. Then if I was interested in the 5th term, then this would be another term. But again, each of the Merlins has one of the qubits. They send them back to me. I measure the energy. And now I have something that makes more sense than before. There's no necessity of checking consistency anymore because I a priori decided how I was going to split the proof in between the Merlins. All right, does this work? Okay, give it away. It doesn't, but here's an example. I think is an interesting example. Call it the EPR Hamiltonian. Imagine your local Hamiltonian is very simple. Each of the qubits is just a spin. And each of these Hamiltonians is trying to enforce that 2 nearest neighbors are in an EPR pair. Thanks. So all the terms look like this, and they're saying this should be an EPR pair, this should be an EPR pair. And then they're saying this should also be an EPR pair, this should also be an EPR pair. So if you think about it, it's a highly frustrated system, right? It's impossible to satisfy all these constraints simultaneously. But I claim that in my game, the Merlins have a perfect winning strategy. Even though it's impossible, the ground state of this system has energy n/2 or something. the Merlins can win in my game with probability 1. And it's very simple how they do that. They only need one single EPR pair. And then whatever question I ask them, whatever Hamiltonian I'm interested in, anyways, I'm going to ask one of them for one qubit and the other for another qubit. And it just always send me back the same qubit, the same EPR pair. And then I check my Hamiltonian, I'm checking it's an EPR pair, and this works out. I'm fully convinced. Right, so the problem is that even though I'm asking each of the Merlins for different qubits, I have no guarantee that in their mind, these qubits are really different. They can always just send me the same thing. So to get back to the picture that was on the first slide, here's the kind of issue that we have. Arthur is trying to examine this picture, but he can only make local observations. And he's opening this window here, and he sees that there should be a human body there, or perhaps a forest. And this should be the front of a house. This should be the sky, and this should be a curtain. And if you look at each of the pictures by themselves, maybe they make sense. To be a little bit more concrete, relate this to my example, here's what Arthur is trying to do. He's opening pairs of windows, and each pair he sees an EPR pair. So there's an EPR pair here, an EPR pair here, an EPR pair here. That all makes sense, right? It's fine to have an EPR pair there, also there. But now, of course, there's no such thing as 4 EPR pairs tied in such a picture like this. And so what we're trying to do is to derive conditions, derive a game under which, from the local observations, Arthur could be able to conclude that there exists a global state that's consistent with these local observations. And so this is what we did. We gave a different game that is going to work. And so now I can describe the result, and I'll tell you what the game is. It's a very simple game. And what this game achieves is that if you're given an instance of the 3 local Hamiltonian that acts on n qubits, then the game is going to involve 5 players, and it's going to have the probability that if there exists a ground state with low enough energy, I'm sorry, I got the wrong normalization here. So this h, think of it as being normalized. So it's the sum of the terms divided by the number of terms, and each local term has norm 1. It's not very important, but if you get confused, that's my normalization. Then there'll be a very good strategy for the Merlins, right? If this is close to 0, this will be very close to 1. But if there was no state with low enough energy, then there will be no good enough strategy up to a polynomial factor here. C is a constant. So the game will look something like this. Arthur now is not interacting with 2 Merlins, but he's interacting with 5 Merlins. And again, I apologize. I just realized that my talk is very male-centric. So, but okay. Well, blame Disney. I'm sorry. So there's 5 Merlins. And they're all entangled, so they have some arbitrary 5-partite entangled state in between them. The questions in the game will actually be classical. I allowed quantum questions earlier, but they'll just be classical. They'll be very simple. The 3 indices sent to each of the Merlins. Everyone gets a classical string, and then each of them is going to reply to me with 1 or 3 qubits, depending. I'll tell you on the last slide. So the messages from the Merlins to Arthur are quantum, but they're very short, 3 qubits each. Before I describe the proof system, just a consequence of this is that it says that when you look at quantum games, then this value, the maximum success probability of entangled Merlins here for the kind of games that we consider, this is a quantity that's QMA hard to compute or even to approximate to within inverse polynomial factors. So in particular, it's strictly harder to compute than the classical value, which is just the success probability, also in the quantum case, but without entanglement. So this is something we didn't know before, we didn't even have evidence for. Another consequence is more complexity theoretic. I just put it up here, but I'll get back to it at the end of the talk. This is only for those of you who know about these. It implies a separation between quantum multiprover interactive proof systems. So here's the game. Arthur is here trying to check his instance of the local Hamiltonian problem, and he has access to these 5 Merlins. And here's what he asks them to do. So they're trying to convince him that this ground state exists, so it's there in the sky. But instead of splitting it directly in between them, he's going to ask them to encode each of the qubits of this state using a very simple error correcting code. So let's just take a 5-qubit error correcting code. The only thing I need is that this code corrects at least 1 error, any code that does this. And so each of the qubits is encoded individually into 5 qubits, and then each of the Merlins get 1 share of the qubits. So they each get sort of a share of the ground state in this way. That's what they're supposed to do. Of course, they can do whatever they want, right? And so Arthur is going to run 2 tests, each of them with probability half. So for the first test, he does essentially the same thing as he did before. He just takes one of the Hamiltonians. This acts on 3 qubits, and he asks everyone for, give me your share of that qubit. So each of them is going to send him back 3 qubits, and then he's going to decode the error correcting code, recover the 3 original qubits of the ground state, and estimate the energy of that local Hamiltonian. That's sort of exactly the same as we had before. And then the second test is very similar. You again select one of the local terms, but now you send the 3 qubits only to one of the Merlins. And all the other 4, you pick one of the 3 qubits and you ask them for their share of that same qubit, each 4 of them. So that's what you do, you get them back. And then, from the 1 qubit that was asked, for the 1 Merlin that was asked the 3 qubits, you trash the 2 that you're not interested in, you keep the other one, and then you check that the 5 qubits that were supposed to be the same you got from the 5 Merlins, that these lie in the code space. So you just, check, make a syndrome measurement or something. And if it doesn't work out, you reject. If it works out, you accept. So that's the game. It's easy to see that it has the so-called completeness property, which is that if the Hamiltonian has a good ground state, a state with low energy, then there's a way for the Merlins to succeed in this game. They just do what I said they should be doing. Then in my second test, they'll always be accepted because they encoded things correctly. And in the first step, they'll be accepted with probability that's related to the energy of that ground state. And if it's low enough, then they have high enough success probability. So the question is whether we can achieve the soundness property. So I'm not going to give you the details, but maybe just to give you a little bit of an idea, maybe a lot of you already have an idea of why this would work in your mind. It's conceptually, it's not too complicated. Let's look at it in the example of this EPR Hamiltonian that I gave you before and see what happens in this new game. The original one didn't work. Why does this one work? So my Hamiltonian was just this thing, trying to project on EPR pairs. I'm drawing the pictures with 3 Merlins, but let's imagine that there's 5 Merlins, right? So let's try to make them cheat, fool the protocol in the same way as they did before. So let's just have them share one single EPR pair, and then maybe they split the shares of this EPR pair in between themselves using the error correction, right? So they apply the code to each half, and they have their halves. And let's say that what they try to do is that when they're asked for a complete Hamiltonian, the 2 qubits, well, they send back both their shares. That's what they can do, right? And then if they're asked just a question that's a single qubit, but it's not part of it, they're not told which Hamiltonian I'm interested in, then they have to decide if they send the first share or the second share. So in order for them to be consistent, let's imagine they always send back the first share. So in the first test, this is going to work out fine, just as before. Any Hamiltonian I'm interested in, both of them are going to send me back both of their share. I'm going to decode an EPR pair correctly, verify this is an EPR pair, things are just fine. Now, if we look at the other test, one of the Merlins is asked a Hamiltonian HI or another Hamiltonian, any of the Hamiltonians. And the others, let's say, are asked one of the questions, for instance, this question QI. So now, if the question to the first Merlin was this term, then the Merlins, they send back their first share when asked their question. This matches the first share that this guy is sending back, so the decoding is going to work correctly, and this will be fine. But in the other case, if the one special Merlin is asked for this term, he again sends back both shares, but then I'm going to check the first share of the other guys with his second share. And that's not going to work out. What would have worked is if I had checked the other guy's answers with the first share that this guy sent me. So they're all confused because they don't know if I'm interested in this term or the other term here. So I'm going to catch them. So this strategy doesn't work. And sort of the reason why it doesn't work, or the way to think about it, is that when I get answers from 4 of the Merlins about a certain particular qubit, QI, by the code property, by the fact that this code corrects one error, these 4 qubit answers, they commit only one possible answer that the remaining Merlin could be given back to me. If I have 4 qubits of the encoding of a single qubit, then there's only one possible way to give me a qubit that's going to match these 4 into, I'm saying this very informally, of course, but there's only one possible way to give me back a qubit that's going to match these 4. And so that's the key property that we're going to use in the analysis. Let's just see a little bit what we're trying to show. So we're trying to establish soundness. So in order to establish soundness, what you have to do is, assuming that there's a good strategy for the Merlins in the game, you want to show that there exists a low energy ground state for your local Hamiltonian. So let's see why this is not so trivial to do, because what you're given to start with is 2 things. well, you're given a strategy for these Merlins, right? So they're sitting there and they have some arbitrary entangled state that's allowing them to win the game. I don't know what that state is. It's a 5-partite state. And then for each question that I can ask them, there's a unitary that they apply on the state, and then they send me back a certain designated qubit, or maybe 3 qubits. For the questions QI, I have unitaries UI that are like this, that, you know, if they applied, and then if I did the decoding procedure, then I would recover the ith qubit of the proof. And then I also have similar unitaries when I ask the Hamiltonian queries. But the thing is, I'm trying to come up in my proof with a ground state. This is a n qubit thing. Where do I get these n qubits from? What I'm starting from is a 5-partite state. There's not n qubits there. There's only unitaries that I can apply and a decoding map that gives me 1 qubit. Let's say I do this to create the first qubit of the proof. Where do I get the second qubit from? And this is the problem, you know, this is why this strategy worked for the EPR Hamiltonian, why they can fool you in principle. There's no guarantee that there's an n qubit state lying there in the sky. The only thing you know is this 5-partite state. And so that's kind of what's challenging in the analysis. If you want to show the existence of that state, you have to show how to construct it, or you have to show existence. And you could try to say, well, there's some wires left here, why don't I apply the second unitary, try to extract the second qubit. Is this meaningful? This doesn't mean anything, right? I mean, he applied a unitary, whatever qubits are left here, they don't mean anything because they're not involved in the game. The game has stopped. I only checked one layer. And so what the proof does is trying to argue using the tests that we're enforcing, the error correcting code, that there is a way to make sense of this. So we give a constructive, we give a circuit, an explicit circuit, that's going to reconstruct a low energy ground state from a strategy of these Merlins. So it's going to show that these n qubits can be extracted from the original entangled state if the Merlins had high success probability. But I'm not going to go into the details. I have a picture here. We're going to extract these qubits sequentially. So the first qubit we get just as I had on the previous slide. Just say, you know, imagine we had asked them for qubit number 1, then we run their unitaries, we get this qubit there after applying the decoding map. Now we want to get qubit number 2. How do we do it? The only difference is that we're going to clean up. So cleaning up will involve applying the inverse unitary, the dagger there, cleaning up the space, and then we're going to run the unitaries for the second qubit, decode, get the second qubit, and repeat this over and over again. So why does this work? You could imagine you have the same problem as I said before. Why is there any reason to think that these qubits here are in a state such that if the Merlins apply their unitaries, then it extracts the second qubit? I know that if I were to apply these unitaries on the original state, it would work out. But there's no way the state here is the original state. Why? Because I extracted 1 qubit from it, right? So even in the case of honest strategies, this is not the original state. And so the way we analyze this is that we use the properties of the error correcting code in order to show that from the point of view of this particular circuit here, once you trace out everything left over there, which is what I'm going to do a little bit later on, then there is no difference in between applying the unitaries in this order or in the reverse order. So there's kind of a partial commuting property that holds that for which you use the code. But I'm not going to go into the details. So that was just a picture. Instead, I want to spend the last 5 minutes just describing some consequences of the result. First to this thing called quantum PCP conjecture, and then to quantum interactive proof systems. So let's look at this quantum PCP thing. So first, let's go back to the Pcp theorem that I mentioned in the first slide. So there's 2 statements that you can make, 2 equivalent statements of the Pcp theorem that you can make. I made both of them in my original slide. So one statement is that given a classical game, completely classical, then approximating the maximum success probability of classical Merlins in this game is a NP-hard problem. That's one statement, which is just a reformulation of what I say when I say Arthur can verify NP languages using the classical Merlins. Another equivalent statement is the one that I gave you with 3-SAT, which says that given a 3-SAT formula, it's not only NP-hard to decide whether it's satisfiable or not, but in the worst case, it's NP-hard to decide whether it's fully satisfiable or at most 90% or 99% satisfiable. And these 2 statements are completely equivalent statements, and I proved this to you in my first slide. It's shown by the clause versus variable game. This is what establishes the equivalence between the two. So that's the classical picture. Now let's look at what happens in the quantum world. And what we saw is that Kitaev's result of QMA completeness for the local Hamiltonian problem, this you can interpret it as a first step towards what's usually called the quantum PCP conjecture. So it was introduced by Aronov et al. A few years ago. And the conjecture is that the hardness of the local Hamiltonian problem can be pushed very far in terms of the promise that you have in between the energies that you're trying to distinguish. So what Kitaev showed is that it was QMA hard to distinguish between energy levels that are separated by an inverse polynomial. The conjecture is saying that it's QMA hard to decide between energy levels that are separated by constant multiples of m. M here is the number of terms in the local Hamiltonian. So the norm, it's the correct scaling. It's the norm of the total Hamiltonian. So that's what's usually called quantum PCP conjecture. What our results I like to think of as a first step towards is a second version of the quantum PCP conjecture, which would be an analog of the first statement here. And this would be saying that constant factor approximations to the maximum success probability of entangled Merlins in quantum games is a QMA hard problem. Our result is the first step because what we show is that inverse polynomial approximations are hard. But constant factor, this is presumably easier, so this is why this is a conjecture. What's interesting about it is that these two were equivalent. This is a natural reformulation of this. This is natural reformulation of this. We don't know anything about any kind of relationship in between these two conjectures. Whether one implies the other or not, conversely, or even weak implications, we don't know. And at a high level, this is because this Hamiltonian versus qubit game that I described earlier, this just doesn't work. That would be the natural way to extend this equivalence to the quantum case. And finally, in the last 2 minutes, I want to give just reformulation of our results in the language of multiprover interactive proof systems. So this is more for the experts, but I have to define a couple of complexity classes. So the class MIP, this is the class of languages that can be decided. MIP is the class of languages that have the following properties. So there exists efficient transformation from classical string x, the input, to a game, gx, so this is from the 3-sat formula to the 3-sat game, except in the language of interactive proofs, we're thinking of the games as being implicitly given. They're described as circuits instead of explicitly in terms of lists of questions. So you're going to see it's going to be a bit strange, but such that if the input is in language, then there's a good strategy for the players, and if it's not, there isn't. And so reformulations of what I had in the previous slide, the Crook-Levin theorem says that this class, when the completeness and soundness parameters C and S are 1 and very close to 1, this is exponentially close to 1, is equal to n exp. And the Pcp theorem is saying that you can get a characterization like this, a consequence of the Pcp theorem. You can improve these parameters to 1.5. So in the quantum case, we can look at the quantum analog of that class, quantum messages and quantum entanglement. Same definition, except now that we're allowing quantum games and entanglement between the Merlins. And what's known about this? So the first thing, this is a result, it's related to the result that I mentioned before, is that we know that this class, and in fact, we don't need the quantum messages, but even allowing entanglement, this class contains the class nexp. So this was proved a few years ago, and then recently, joint work, or last year, joint work with Ito, we showed that you can improve the parameters here, just as you could for this variant of the Pcp theorem. And so the result, just to frame it in that context that I presented to you today, it's saying that you can go beyond this result, which is something surprising to me. I mean, I didn't expect this to be possible. Not only this contains an exp, but actually it contains a presumably larger class, QMA exp. So it's proving a separation between this class here and this class here, which by these two theorems is equal to this class here, which by Kobayashi Matsumoto result I presented earlier is equal to this class here, is proving a separation between these two. So it's showing that entanglement between the Merlins, you can use it to your advantage, to your strict advantage. It's not only something that they can use them to achieve correlations that will fool your proof system or your game, but you can use it to your advantage to verify more complex languages. And I'm out of time. Let me summarize very briefly. What I described to you is what I, very informally, I would say, call a truly local verification procedure for local Hamiltonian problem using this language of multiplayer games, and it demonstrates that entanglement between the Merlins can be useful. And the proof uses just very simple, really basic properties of quantum error correcting codes in order to show that successful Merlins, if Merlins are accepted in the game, even though I'm only getting very local pieces of quantum information, there should exist a big state somewhere in the background in their mind that I can in principle reconstruct from their answers. So there's a lot of interesting questions. One of them is, can we do the same thing but with a completely classical game now? And there's no objection to that. In my game, I required qubits. This seems very important in the game, but it could be that you can design a different game for the local Hamiltonian problem that has completely classical interaction. It would require the Merlins to use their entanglement, of course. Another question, but that's perhaps a bit harder, but okay. Interesting question is, what is the relationship between these two conjectures? I don't think this has been looked at so much. I think it's a very intriguing question. You could make some nice discoveries just by looking into it. And kind of a crazy question is whether we can push these beyond QMA. Now, I showed you quantum games for local Hamiltonian problem, but as far as we know, there's no limit to the power of these games. You could use them to verify languages that go beyond QMA. I have no idea if this is possible or not. It sounds a bit crazy, but maybe. So thank you.
So we have time for a few questions. First, start with Ronald.
So you're using 5 Merlins here because that's sort of the minimal number of qubits you need for an error correcting code.
Right.
Could you cut the number of Merlins by using a quantum error detection code?
Yeah, probably. So I think you can do that using 4 qubits. So it would be 4 Merlins. I think this is likely. I haven't checked carefully, but it's likely. Yeah.
So actually I had the same question, but I can comment that if you can do it with error detecting codes, then you could actually go down to 3 Merlins by using a Qcrit error detecting code.
Okay. Okay, so that's...
But you still need to use the error detecting
5
codes.
to 4 was not enough motivation for me to spend the night doing it, but 5 to 3, okay. Let's check. Okay, thanks for the observation. Well, we can... I can ask you later. 2 is very interesting, by the way, because these results that I showed you before, some of them on the earlier slide, even prior work, requires 3 Merlins. And although I'm not surprised, 5, 4, 3 seem to be kind of equivalent. As far as the state of our knowledge is, could be significant differences between the usefulness of 2 Merlins and the usefulness of 3 Merlins. So achieving similar results with only 2, I think that is interesting.
I guess I have a question about that last point. So in terms of areas where we know that 2 Merlins are weaker, so we know it for XOR games and for non-signaling assisted games, right? But we don't know it for entanglement. There's no evidence for it in terms of entangled games, right?
Oh, we don't know it for sure, you mean? I think for no signaling, we don't know for sure either. So sorry, I didn't understand exactly what's the question. If we know for sure, or if we don't...
just besides failing to prove hardness, if there's any, other signs that 2 might be easier.
I don't know. I mean, the sort of colloquial thing is to say, well, monogamy or something. So some of these proof systems, the way they use the fact that you have many Merlins is to weaken the ability that they have to use their entanglement by taking advantage of the fact that it's harder to share, EPR pairs between 3 Merlins. So that's just trying to take advantage of monogamy. But that's very informal. So yeah, I don't know.
Okay, if there are no more questions, let's thank Thomas again.